Hello, Suzanne. We can't hear you. You are on mute.
Okay. Should work?
Yes, we can hear you. We see you.
So up. I have this. Okay. I think we have a few minutes.
Yes, let's wait because there was a keynote before. I'm not sure the keynote is
finished. Yes, I left the keynote earlier.
Yeah, me too. It was not ended. So
You.
we will
Okay.
see when all people will come. It means that the keynote is over.
Yeah, for the moment, there are not so many. Yeah. Who's the first? Okay. First speaker is here. Okay.
Hello, Suzanne.
Hi.
Just wondering the order of the speakers.
It looks after the session definition, you are the first.
Oh, I'm the first. Okay.
The CapOS, it's the CapOS talk.
Yeah.
Yeah. Okay. You're the first.
Okay.
Rosa. Okay. Venza. Okay. There is not all speakers are here. Arthur, Jean-Baptiste. Yes. Okay.
Can you see the screen?
Yeah. Yeah. Can see the screen, but we should make a moment. There are not really many participants now. Yeah.
I think they are in the Town room, but hasn't got in the Zoom yet. No.
Ah.
I'll go talk to them.
Yeah. Good idea. That people get conscious of the fact that they should come to the Zoom meeting. There is still one speaker missing, Rezvana. I cannot see. Bon, let's hope.
Yeah, she's still in the Canada, but I can't talk to her. Let me see if I can chat.
Ah, yeah, here, perfect.
Okay, great.
Okay, everyone is here. So maybe should we start? Also, if there are not so many people here, but I think we should keep the time. So welcome to this sixth EMSOFT session on power, energy, and analysis. The first talk will be by Jongouk Choi, who is assistant professor at University of Central Florida. He will talk about CapOS, capacitor error resilience for energy harvesting systems. And I think you should now share your slides. And you have, let's say, 12 minutes for your talk, and then we should have a little bit of time for questions.
Yeah, thanks for the introduction. My name is Jongouk Choi. I'm from University of Central Florida. Today I'm going to introduce one of my research topics, CapOS. This work has been done with my colleagues, Dr. Joe from ETRI, one of the national labs in South Korea, and Dr. Zhang from Purdue University. Then let's get started. IoT market is growing. A trillion number of IoT devices are spreading all over the world, even in Mars. However, powering these IoT devices is a pressing challenge. It is not feasible to change the batteries of billions and millions of IoT devices out there. This has brought a tremendous amount of interest in energy harvesting technology to self-power the devices using ambient energy sources for free. In fact, we are all surrounded by free energy sources: Wi-Fi, solar, motion change, and even your body temperature can be the energy source for the systems. And the lack of batteries can further enable the system design much lighter and smaller. However, there is no free lunch. Energy harvesting systems have one critical challenge, which is that ambient energy sources are unreliable. Here are power traces collected from different ambient energy sources, such as radio frequency, pressure, solar, and temperature. And no matter which ambient energy sources you choose, as you can see, the resulting power is unreliable, which causes frequent power failures. Because of the frequent power failure, the system can lose data and fail to complete the program. Let's say we have a timeline of program execution. In the middle of the program execution, we have a power failure. Then the system loses all volatile data and it starts all over again, cross power failure. To address this power failure problem, energy harvesting systems use a small capacitor as energy buffer and integrate with non-volatile memory as main memory without having any cache to preserve data across power failure. Let's take a look how energy harvesting systems work across power failure. They first collect ambient energy into this energy buffer. When the buffer is fully charged, the systems start to run a program. The systems continue the program execution until the buffer energy is depleted. When it's depleted, they hibernate to recharge the capacitor. In other words, energy harvesting system intermittently compute only when enough energy is secured in the capacitor. For intermittent computation, the state-of-the-art introduced the roll-forward recovery solutions with just-in-time checkpointing mechanism. that checkpoints volatile registers to non-volatile memory at impending power failure point by leveraging voltage monitoring system. Let's take a look how it works briefly. On the left-hand side figure, we can see capacitor charge and discharge graph in a given frequent power failure situation. The voltage monitoring system detects impending power failure at a certain voltage threshold. It signals to core, and the core checkpoints volatile registers to non-volatile memory and power off. Then in the wake of power failure, the capacitor is fully charged. Voltage monitoring system sends the signal again to the core. Then the core restores checkpoint registers from the non-volatile memory and resumes the interrupter program. However, we found this mechanism relies on the capacitor too much, assuming the capacitor is always stable. However, it's not true. It can be cracked, damaged, and degraded due to some stressful conditions such as high temperature, humidity, overvoltage, continuous charge and discharge condition, and ripple current. And due to this reliability problem, the capacitor cannot hold a sufficient amount of energy to checkpoint all registers to non-volatile memory at the impending power failure point. Originally, the just-in-time checkpointing is triggered at backup voltage threshold, assuming that we have sufficient amount of energy to checkpoint data during power loss. However, capacitor is gradually degraded. As you can see in this slide, the capacitor can be degraded more than 10% within a week in this case. If it detects impending power failure at the same voltage level, the amount of buffered energy is less than it's supposed to. Then with this insufficient amount of energy, the just-in-time checkpointing can be failed, losing data across power failure. This can cause wrong recovery problem across power failure. We define such a problem as capacitor error. To address this capacitor error, we introduced the CapOS, operating system-driven capacitor error resilience solution. CapOS can detect the capacitor error without causing wrong recovery problem. Upon the detection, CapOS changes its operating mode to ensure forward progress if the capacitor is degraded. To address the capacitor error, one might suggest to leverage proactive detection mechanism by increasing the voltage backup threshold. It might be able to ensure safe checkpointing with the degraded capacitor. However, the proactive mechanism cannot be a practical solution because the energy in this guard band can only be used for checkpointing, not for forward progress at all. Also, it causes lots of unnecessary checkpoints for performance. And on the other hand, the reactive solution is also impractical because it detects the capacitor error problem after the power failure happens, leading to the wrong recovery problem eventually. In other words, the solution cannot prevent data loss from the capacitor error. Okay, let's move on to address the capacitor error. We add the ACK to the last part of the checkpointing protocol as barrier of just-in-time checkpointing. And let's take a look how it works. Let's assume the capacitor is degraded and the voltage monitor detects impending power failure at the backup voltage threshold, then checkpoint volatile registers to non-volatile memory. Here, CapOS tries to checkpoint the ACK to non-volatile memory as well. In this case, we fail to checkpoint the ACK only, preserving all other data. This is possible because the capacitor is gradually degraded, not cracked all of a sudden, meaning that checkpointing fails to persist the ACK first when the capacitor error occurs. Then in the wake of power failure, CapOS restores corrupted ACK but keep all registers in safe. In this way, CapOS can detect capacitor error and ensure correct recovery. And so far, we have discussed how CapOS can detect capacitor error. Now I'm going to introduce how CapOS can address capacitor error after detection. Unfortunately, the Bohrer recovery solution cannot ensure correct recovery. This is because the solution completely relies on the capacitor, and the capacitor can be degraded more as the condition would last. Then it eventually causes checkpointing failure and wrong recovery problem. To ensure correct recovery, we must enable rollback recovery that can be done without requiring the capacitor. However, it is challenging to dynamically switch from roll forward to roll back recovery because of two reasons. First, the rollback recovery solutions generate a recovery series of code regions. They secondly insert some memory logs and checkpoint stores instead of recovery points. It means the system must have at least two different versions of a program, one for roll forward and the other one for roll back, which cause synchronization issue and performance overhead. Second, switching the recovery mode must be done at arbitrary time. That is, we must be able to trigger the rollback recovery solution, not necessarily at the region boundary. For correct recovery, we should have tracked all memory updates and logged them somewhere in case of recovery mode change at arbitrary time. If you just simply switch the rollback recovery mode without tracking memory updates and leaving logs, it cannot ensure correct recovery across power failure. To switch the recovery mode without causing the wrong recovery, CapOS leverages timer-based checkpointing and Capacitor with the memory protection unit as a boundary-free recovery scheme. Once it detects a capacitor error, CapOS can seamlessly change the recovery mode. In the rollback recovery mode, CapOS enables the timer-based rollback recovery instead of using the boundaries. CapOS set the recovery point at each timer expiration. Within the timer interval, CapOS uses copy and write that can naturally track every memory update and logs original pages on the fly. If power failure happens, CapOS can roll back to the checkpoint point and resume the interrupted program, ensuring safe recovery. To see the impact of CapOS, we have done our experiments by using current community microprocessor MSP430. One is for target board and the other one is for power supply board that can produce some power through GPIO pins. For realistic evaluation, we use power trace collected from real radio frequency energy source. For performance analysis, we estimate the throughput of each scheme by counting the number of task completion times during a day. We set the initial value of the prior works called Samoid throughput as a baseline. When the capacitor has no reliability problem, CapOS shows almost 100% throughput compared to the baseline. We also estimate the throughput of each scheme with the degraded capacitor. When the capacitor error occurred, roll forward recovery solution, so-called Samoid, could not provide any service at all. It's like a denial of a service problem. On the other hand, CapOS and Chinchilla, which is another type of rollback recovery solution, could continue to make a forward progress. In particular, CapOS could provide a 60% higher throughput compared to the Chinchilla. As a conclusion, the CapOS can detect the capacitor error without causing wrong recovery problem. We defined the capacitor error for the first time in this word. Thank you for your attention. I'm happy to take any question.
Thank you for the talk. And are there any questions in the room? Yeah, Claire.
Yes, thanks a lot for the presentation. It was very nice. If I understood, yeah, you make it pedagogical, thanks. So if I understood well, regarding the problem of capacitor aging, you want the threshold to be above the initial one. You want the threshold to be adaptive, if I understood. So how do you compute this new threshold and how do you adapt the value over time?
Oh, that's a good question. As a default setting, we set up the threshold when we check, because we need to checkpoint the voltage registers non-volatile memory in a fairly atomic manner. So we had like a safety net, like a 10%. By considering the temperature increase, another environmental setting differences. So let's say we have 10% safety net, and that's always there. And then with this amount of the energy, we are always going to complete our just-in-time checkpointing for entire register file. But because we need to checkpoint the ACK, so we need to add a little more energy in this energy budget. We can assume, oh, this is ACK message, which is really trivial compared to the entire register file. So even if you just add like a 5%, that's energy consumption of the ACK message compared to the total energy consumption for register file checkpointing. If you just add this 5% more, that could be the energy consumption overhead. But this is again, really trivial compared to the rollback recovery solution, or if you think about the impact of a CapOS or capacitor error, then this is trivial and energy efficient solution, we believe.
Okay, thank you.
No problem, thank you.
Okay, so I think we have almost exhausted our time budget. Thank you very much. I think you should now unshare the screen. Yes, done. Next speaker is Rose Bohrer. She received her PhD last year from CMU, and now she is she's an assistant professor with the computer science department of Worcester Polytechnic Institute, and she will talk us about cyber physical verification of intermittently powered embedded systems.
Great, thank you. Is the screen sharing and the sound okay?
Seems to work.
Okay, great, thank you. So I really like that our two talks were Maya and Jongouk's talks were in the same section, because I think they mesh together in a really nice way. So although I'm also looking at intermittently powered embedded systems, I'm focusing on kind of a very different starting point, which is to see what we can learn from the world of cyber physical systems verification and how we can kind of bridge that to thinking about these intermittent systems. So I can keep my description of intermittent systems short because we just had a very good introduction to them. So an intermittent computing system, for my purposes, is a system where you have no power cord, you have no battery, you are just using some energy harvesting device to immediately harvest energy from your immediate environment, store it in some small capacitor for a very short amount of time, and then quickly use it to do your computing tasks. And one reason that we care about getting these systems correct is because it turns out they're useful in a whole lot of different systems where safety and correctness are really important. So one system that I'd use, you could say, I'm going to use this, you could say maybe as a toy example or just as an illustrative example, is to think about a scenario where perhaps we wanted to have a temperature monitor that monitors the temperature of COVID vaccines in cold storage. The idea being that if it got too hot, they would spoil, and that would be a real social good that's lost. There are a bunch of other applications that are not hypothetical that people are working on now. Anything from medical devices that are very small, where you don't want to lug a battery around on your body, to traffic monitoring systems where delay in traffic reportings could really have effects on safety or efficiency. And I think one good example is because it's very time critical, would be any sort of fire monitoring or building safety monitoring system, right? If there's a fire in a building, it's very important to detect it immediately so you can do something that's safe. And so because safety is so important for these systems, we want to think in this paper, how do we take these intermittent systems and reason about their safety? But we're not just reasoning about kind of these aspects around restarting, whether we have enough energy, whether we need to restart, whether we can checkpoint correctly. The kind of safety properties that come up in these examples, we also very much care what's happening physically. So is the fire going to spread? Is the vaccine going to spoil? This is sort of a different layer in the technology stack. And I do want to be clear, this is not an either or, this is a yes and situation where there are many different tools we want to have working together. In fact, if we want to look at kind of the long-term goal for this line of work, my starting point is to look at the technology stack for doing verification about cyber physical systems. Cars being one example, but really any system where the code and the physics and the interactions between them are really fundamental to telling whether it's safe. So kind of the most fundamental layer of that stack, you could say this is everything from compilers to runtimes, making sure low-level things are implemented correctly. The next layer up is what I'm going to focus on. This would be called hybrid systems verification, where you perhaps have some dynamical model with differential equations, you perhaps have some code model, and you want to reason about what this model's physical impacts will be. And then if you want, this is a model, it is an abstraction. If you want to take that abstraction to an implemented system that you can deploy in the real world, there's a few things higher up the stack, like code generation or runtime verification approaches. And if we look at CPS in general, there's a very nice story for this technology stack. There's a lot we can build from. And so I want to bring this into thinking about intermittent systems. The problem, of course, is that intermittent systems immediately pull the plug on this technology stack. because cyber-physical systems verification has always assumed that we have continuous access to energy. And so what we need to do almost as a community is to get these systems safe. We need to think, how would we rebuild this whole stack? How do we get each of these kinds of technologies to accept intermittence? And if we look at the first stage of the stack, things that deal with things like compiling code correctly, implementing runtimes and operating systems correctly, there's solid work on this. Jongouk's work, the talk before me, has some great contributions to this. Some of the other ones that we were citing were things like the work of Lucia et al., so Capybara and others. But what I want to do is, because I trust other people to do this job, I want to focus my attention on this other job in the stack. And that's where this paper comes in. So what this paper is doing is it's investigating hybrid systems verification for intermittent systems, specifically through a version of hybrid systems called hybrid games. And the way that we did this is by doing a programming language design and a prototype implementation of a language for modeling these systems and reasoning about their correctness. That language design and its tool are both named Batfly. And the way this works, as we'll start to step into, is we build on this tradition of task-based programming and task-based modeling for intermittent systems. And then you can build a task-based model that incorporates not just the code, but the physics. And then you can state what it would mean for this task-based model to behave correct, not just in the sense of correct code, but also in the sense of correct physics. In the example that I'm showing on the upper right, an example of a correctness property might be that if one of the states I've modeled is that it's possible for vaccines to spoil, then my theorem that I want to prove might be, at all times, it is true that I'm not in a spoiled state, and at all times it is true that my temperature is less than 8 degrees Celsius, the temperature at which we would consider this to have spoiled. Okay, and so we can state these properties that are really fundamentally about physics, but really fundamentally talk about whether our code is doing its job as well. So let's dig a bit more into what I would call my toy, or let's say my educational example. So if we wanted to think about a temperature monitor on a COVID vaccine cooler, this is going to have three kinds of dynamics we need to model. It's a game, it has discrete things, and it has physical things. So the game aspects of this are that there are some events in the system that are out of our control, and we need to assume these will happen at the worst possible time. So for example, the person who's distributing the vaccines might always open the lid of the cooler at the absolute worst possible time, causing these things to warm up. On the discrete dynamics, there are many discrete decisions that influence our control code, but also influence correctness. So if we have sensors, such as temperature sensors, then we need to check when are we going to choose, when are we going to actually sense the temperature? What frequency will our sensor run at? We also have these little capacitors that store energy. In fact, we're looking at cases where you may even have multiple. And so we also need a policy that says, when I'm going to charge energy, how long am I going to charge it, and which capacitor am I going to put it in if I have more than one? These systems are often networked, and so we may also need to make choices such as how often to communicate and with whom, using how much power. All of these discrete dynamic choices will need to be influenced by our understanding of physics. In this case, our physics would be your traditional linear Newtonian heating law. So whatever temperature our vaccines are exposed to, they will heat at some exponential rate. And then if we have a physical notion of safety, we can work backwards to figure out what control policy is needed. And so I'm not going to dig into every line of the model. For that, I would recommend the paper, but I do want to give a quick idea of how this model would be set up. First of all, it's divided into major tasks, which represent major states that your code could be in. So on the left, we might have two tasks where that represent our actions in the games. So during my turn of the game, sorry, I need to go back up. During the part of the game that I control, I get to make this choice of whether I want to sense at a slower rate or sense at a faster rate. And after some amount of time, the lid will be opened, and that will now be out of my control. So I don't get to make any more control decisions during this alert phase. And I need to control things in such a way that after the alert happens, we will not get to the spoiled state. Specifically, there's a timer that elapses, and if I wait long enough, we're going to say that the person we alerted has come and helped reset the system to its good state. And so within this, there's a lot of discrete dynamics. So all of the lines in blue are writing for each task that we might be at, what are the conditions that tell us whether to switch to another task, and if so, which task to switch to. So in the first task, the slow task, we might wait until a clock reaches 24 hours, so 60 times 24. And then after that time, we might decide to switch either to a fast state or an alert state, depending on the timing. In another state, such as in the demonic alert state, well, actually, it's going to be the daemon that gets to pick what to do. Our opponent will pick, if enough time has elapsed, it's allowed to switch. Sorry, if it has gotten warm enough within a certain time, it's allowed to tell us that the system is spoiled. Otherwise, when we reset to kind of the healthy state, the opponent gets some amount of influence over the exact temperature. So they can set it to the worst possible temperature for us. There's also some other details going into the language, such as how many capacitors there are, what their minimum and maximum capacities are, and what all the initial values of variables are, all of which then fits together to let us prove the safety theorem of our choice. So I talked a lot about the language in this talk, but one of the most important contributions is that after you've written this language, you can then export it to existing proof tools. So you can export this and use a tool called Chimera X for the backend proof. And one of the important contributions is that we have outlined a proof paradigm that you can use sort of in general for these style of proofs about system safety. And the idea goes back to this same idea of energy budgeting that came up in Jongouk's talk. This idea that you need to know how much energy you'll need in the future and how long it will take you to save up that energy. And so we can frame this as almost a model predictive control problem where we say, I'm going to look ahead at how much energy I need in the future, and I want to write a control policy that gives me enough energy now to meet my future need. Now, in this bit of an abstract or idealized model, we get a very strong theorem about this, which is if we certainly have enough energy, we can ensure that we actually never have an uncontrolled power loss, okay? And if we can get this strong guarantee, then we allow the entire rest of the reasoning to use kind of well-established techniques that would be used for a non-intermittent cyber-physical system, because we've essentially showed a non-intermittent behavior. Now, for anyone who works in the area, you'll say, okay, but that's not the reality. And I will finish this up real quick because I've got an eye on the time. So if that's a bit idealized, then how do we take this from something ideal to something you could use in the real world? There's two approaches. The first part of future work is to take this hybrid verification approach and plug it into the rest of the stack that has been built for verifying and producing correct cyber-physical systems. So building on existing technology for code generation and runtime verification to go from an ideal model to something working in practice. The second thing that we can do is we can acknowledge that the foundations need to account for the complexity of these systems. In reality, these are often distributed systems, and they are certainly very stochastic systems, right? It's a very non-deterministic behavior, how much energy you'll have. And so by incorporating these into that proof paradigm and into this modeling paradigm, you can then get a system that'll have an analysis talking not only about the case where you prove the absence of restarts, but also reasoning about cases where restarts would be inevitable. And that is it for my slide deck. I'm happy to switch over to questions. Thanks for your attention.
Thank you very much for this nice talk. So are there questions in the room? Otherwise, I mean, I have one. So in fact, the feasibility of this approach more or less depends on how well you can model the amount of available energy that you can count on. If you have little knowledge about this, I mean, verification seems out of reach. If you have good knowledge on this, this looks much more feasible. Isn't it a way of kind of summarizing what you're telling us? I mean,
correct, and I would actually say that's why this runtime monitoring story becomes so essential, because part of what the modern monitoring tools will do is as you do your proof, you can kind of pull out what are the assumptions that are really essential to correctness. So what are my assumptions about current and future energy dynamics that are essential to getting this to behave correctly? Once you have a runtime monitor for that, you can run your tests, run some experiments, see are these good assumptions or not, If they aren't, treat it as an iterative design and development process where you would go back, iterate your model until you have assumptions that are realistic, that do hold up, and that you do have real world safety.
Yeah, so to say, so yeah, I mean all these alert systems, clearly, if you don't have the energy, you cannot alert. And yeah, voila. So somehow, yeah, it depends on having enough energy for the kind of alert systems you have. Yeah. Okay. Other one, I think, yeah, we have if there is a small question, I can. Otherwise, Claire.
Yes, thanks for the talk. I have a quick question. You have designed a new language to model your system. And my question was, why do you need a new language? Why existing ones were not sufficient?
Good. So I think the easiest way to summarize the answer to that is that one of kind of the mathy contributions in the paper is that we take this language and we translate it correctly to another existing language, which we then use in the backend tool. And what we found, that translation, you absolutely can do it, but it significantly increases the complexity. And because, kind of as Susanna said, it's so important to get the models right, we felt that kind of the expressive power is really an important part of the story. So we wanted to design a language where we'll be able to be more confident that we can start with the right model. And then if we translate and the proof tool sees something more complex, that's okay, as long as we can be confident in our design.
And just the tool that I don't know it.
Oh yeah,
is it based on the hybrid automata? It's based on hybrid automata?
So this particular tool is called Chimera X. It's phrased more as a theorem prover rather than a model checker. And it uses a programmatic notation. So, but the programmatic notation that it uses is completely equivalent to hybrid automata.
Okay, I get it. If it's a theorem prover, it's a bit complex. I understand your point.
Okay. I think we should, because we have short slots, we should.
Understood.
Thank you very much. We should switch to the next one, which is given by Wen Zhang. Is she or he is here?
Yes.
Yes. So I think you should share your screen. So she is from yeah, okay, maybe you will introduce yourself. I lost it for the moment. You will talk about sparsity-aware intelligent spatiotemporal data sensing for energy harvesting of IoT systems. Okay?
Yes. Okay. Thanks for your briefly introducing. And can you see my screen? Okay. Okay. Hello, everyone. I am Wen Zhang, from a PhD student from Texas A&M University, Corpus Christi. Today, I am very glad to present our paper, Sparsity-Aware Intelligent Spatial-Temporal Data Sensing for Energy Harvesting IoT System. So as we know, with the development of artificial intelligence of everything, various embedded devices are deployed at each corner of our world to provide observations of our life and on our Earth. However, because powered by batteries, those devices has a limited lifetime. Under such background, energy harvesting devices that harvest energy from ambient environment to power the onboard executions becomes a promising solution to substitute the battery-powered devices as introduced by previous talker. Because of the transient nature of the energy harvesting device repeats the execution and sleeping in an endless cycle. Moreover, as the uncertain and weak power supply, energy harvesting devices work intermittently and might be interrupted by power outage, especially when the workload is too heavy, such as so many devices has to collect a huge amount of data and then uploading those data to the server. The communication is very the energy cost is intensive, the devices will be interrupted frequently, which degrades the data collection accuracy and efficiency. What worsen is that energy harvesting devices even haven't sufficient energy to complete those tasks. Therefore, to reduce the needed data, we adopt the sparsity-aware data sensing. Based on the compressed sensing technology, most data of our life, such as images and audios, are compressible. So the critical feature of the collected data actually are captured by the sparse vector. The full state data X can be reconstructed from the sparse measurements. Therefore, while most papers are studying how to improve the data quality, such as obtaining the high-resolution images, and then throw out most information during the uploading to the server, because the data will be compressed. In our paper, we apply the sparsity-aware sensing. So that means we only sample the sparse raw data Y that capture the critical feature information, and then obtaining the full state data by reconstruction. So even that the sensing is sparse, because of the intrinsic intermittency of energy harvesting devices, it is highly possible that energy harvesting devices might be sleeping when we need to sense the critical data. So that will lead to the failures on the feature capturing and further lead to the poor performance on reconstruction. So this data missing will get worse when the collected data are spatial temporal. That is the 4-dimensional data with a huge data size. So what is the spatial temporal data? This kind of data mainly provide the Earth observation, such as water data. It has 3 coordinates, latitude, longitude, and time. Also have 1 attribute data, such as what is the air density at this specific location and time. This picture visualizes of an example of the raw spatial temporal data sensed by a 9x7 grid of devices at different latitudes and longitudes, where different snapshots represent the spatially distributed data at different time points. For each snapshot, the cell in the grid indicates the data of 1 device. The data at the same location in different snapshots represent the temporal data of 1 device. We named it as trace. Therefore, the spatial temporal data are composed of either a set of snapshots at continuous time points or a set of traces at different locations, or say at different devices. So the snapshots capture the spatial features at different time points, and the traces capture the temporal features at different devices or say locations. Therefore, we can conclude that our research scenario is, as the right side picture indicated, it is a 3-layer ERT system for spatial temporal data collection. In the bottom layer, the ERT devices harvest energy from the ambient environment to provide the power supply for the onboard local sensing, local computing, and the communication. The ERT devices sense and transmit the data to the ERT server for pre-processing by the wireless link. The ERT server and the cloud server will reconstruct the sensed and sparse data. Therefore, this paper aims to schedule sparse sensing on energy harvesting devices with the consideration of the potential interruption. And then through the collected sparse sensing measurements, the full state data are reconstructed. Our goal is to minimize the reconstruction error. That means when we consider to decide which time point and the location data should be collected, we need to optimize the sensing schedule from both spatial dimension and temporal dimension, so that the spatial features and the temporal features can be captured simultaneously. The reconstructed data should be as similar as the real collected data. So To conduct the sensing scheme, here is our method. We first retrieve the historical data from the database, and then extract the temporal eigenmodes and the spatial eigenmodes, and from the historical data. And so each device has a precise TPL to represent the temporal features at each time point, the precise SPL to represent its spatial modes. After that, based on this eigenmodes, we can conduct a fixed scheme. That means we can extract, we can identify which time point is pretty important for reconstruction. So, so for each device, from temporal perspective, have a local scheme, and there is a global scheme from the spatial perspective at each time point. And after that, we will do all calculation to conduct a fixed overall sensing scheme. As mentioned earlier, because of power supply of energy harvesting devices, the fixed scheme works not as good as expected. Therefore, taking this fixed scheme as a suggestion or set as the input, we use the deep reinforcement learning to fine-tune the runtime sensing scheme. Each device has a deep reinforcement learning agent to dynamically decide if sensing or not. And then the sensor data are transmitted to the server for reconstruction. The average reconstruction error for one sensor is calculated, and the feedback as a reward signal to the deep reinforcement learning agent for the neural network optimization. Because if we always perform the sparse sensing all the time, there is no full state data. We cannot identify the reconstruction performance because we do not know what is the full state real data. Therefore, the full state data will be uploaded periodically for the model validation and optimization. So we implement our proposed algorithm as agents and compare it with 4 baselines. We simulate to measure the solar irradiation in over the United States, where 343 devices are deployed to sense per 5 minutes. So we randomly select 2 devices at different locations to visualize the reconstruction details of 3 baselines. The green indicates the real data, and the blue is reconstructed by the real collected data. That is sparse, as the picture indicated. Ideally, the reconstructed data are expected to exactly coincide with the real data. Meanwhile, the fewer data we collected, the better is. So specifically, the irradiation value of the collected data at -1 indicates that the sensing at that device or say at that time point is skipped. So we can see the sense is sparse. As we can observe, only the S agents can capture the features at 16 o'clock. So here is the 2 example snapshots at 10 o'clock and 16 o'clock, which should show the special features. Because those devices' location is very close, so the special features did not indicate obviously, but we still can observe the S agents is better than the baselines. So although S agents achieve the best performance among the baselines, its overhead is slightly higher than other methods because it needs to run the neural network at runtime. So I think here is all of our paper. So thanks for your listening, and I am happy to answer any questions.
Okay, so we have, thank you for the talk. And we have time for a very short question. If there is a very short question. Yeah. Claire, thank you.
Yes, thanks for the presentation. So a quick question about your training or learning with reinforcement learning. What kind of what kind of technique did you use to make? So you use a time series. What did you use technically to make this training?
Okay, we use the DQN as the underlying to train as the deep reinforcement learning method. Yeah.
Yes, but the traces, you took them as a time series and you use time series results. What did you use concretely?
Okay, you mean like we have a time series something, how to deal with it, right?
Okay, I will read your paper. Thanks.
Oh, I'm sorry.
Okay, so thank you. I think we have to switch to the next talk. The next 3 talks are very short talks, so we have to respect the time frame. So the next talk will be Reswana Mamata on a resource-aware optimization model for real-time systems, analysis and design. So you are here, you may share your screen.
Okay, can you see my screen?
I see your screen. We would need your slides.
Yeah.
Yes, wonderful.
Okay, thank you everyone. I am Reswana Mamata, and me and my supervisor worked on a resource-aware optimization model for real-time systems analysis and design. So our research objective was to find the minimum possible resource allocation while maintaining the deadline requirement of each task. And we used it based on the supply and demand bound function. And these functions are nonlinear functions. So we formulated the resource allocation problem as an optimization problem. So supply bound function actually specifies the minimum possible resource supply guaranteed by a system at any time period t, and the demand bound function actually represents the maximum possible resource demand at any time interval t. So a work will be schedulable if the SBF is greater than or equal to DBF at a time point t. So our optimization model, OPTRS, is formulated as we want to minimize the supply and demand bound function difference at hyperperiod h, and we want to make sure that in every point t, the supply bound function is greater than or equal to the demand bound function. And the resource supply will be less than or equal to the period, and our decision variable here is the resource allocation, which is theta. We evaluated our proposed resource-aware optimization model using a dataset on digital avionics system from the Arvind et al. Work, and it has like 5 components, and the workload specifications, the period PI indicates the period and EI execution time, and we have considered that the period for the resource will be 10, and we want to identify what is the minimum possible resource allocation for these workloads. And we have found that, and we also compared our method with like the SBF and DBF function has a linear functions like LSDBF, linear supply bound function, and linear demand bound function. Based on that, we can calculate what could be the resource at a time t, and we compared our work with that using those equations, and we can see our method has an average of 30% reduction in resource allocation compared to the LSDBF based equation based resource allocation. So, and our future work includes like we want to integrate other scheduling algorithms. In this case, we have used the EDF, and also considering delay while calculating the resource allocation for firm real-time systems. So this time we only considered for the hard real-time systems. Thank you.
Thank you for the talk. Is there a question in the room? Just one short question. yeah, I mean, otherwise, okay. So well, I understand there is work on these optimizations here. I did not understand what was exactly the technique that you applied to make the to optimize your.
We applied the optimization algorithms available in the.
Yeah. So you suppose you have correct models of what is available and what you have. I mean. Yeah.
Sorry.
Yeah. I mean, you can optimize, but you need also correct models of what. I mean, you must suppose that you have correct models of your supply.
Workload?
Of the workload and the supply bound function. So
yes.
Okay. Okay. So yeah, I see. Thank you. And
Thank you.
I suppose we will have to switch to the next talk, which is by Arthur Grisel-Davy from University of Waterloo and about boot sequence integrity verification with power analysis. So you will share the screen? Yes, wonderful.
Hi, so I am Arthur Grisel-Davy, and I will be presenting today our work on leveraging power side channel information to enable firmware verification on embedded systems. Embedded systems are classically protected against intrusion using two main types of IDS, intrusion detection systems. HIDS, host-based intrusion detection systems, sits on the machine to protect and have access to all the resources, all the relevant information, but they are also at risk of being bypassed by an attacker. On the other hand, NIDS, network-based intrusion detection systems, sits on the network and are less likely to be bypassed by an attacker, but they also have access to only network information. Our new solution aims at providing a complementary IDS that is based on physics. So power analysis is well established for side channel attacks, but we can also leverage the same techniques for side channel defense. The power consumption can be easily measured with a shunt resistor on the main power cable of a machine, and this enables this approach to be applied to any embedded systems that consumes electricity. Let's take a look now at the boot up power consumption for a switch. So in this figure, you can see two power traces corresponding to two different firmware versions on the same switch. The x-axis is the time and the y-axis is the power consumption. And you can notice that even though both firmware are valid and provided by the manufacturer, the differences in their code generate different power patterns. In this case, it is mainly the timing of the execution that is affected. A difference in power consumption can be linked to a number of different root causes, such as a firmware change, a hardware change, or even just a configuration change. And we want to detect all of them to prevent potential attacks. So knowing these power patterns, we can now design an anomaly detector based on the power consumption. So the detector should be able to train on a reduced number of valid traces only, because in a production environment, it is unrealistic to impose downtime to collect thousands of boot up traces or to deploy malicious code on a device, obviously. So for training, we collect only 10 valid traces, and we compute the distance from each trace to the average trace. The distance threshold is defined as 1.5 times the interquartile range for all the distances to the average. So now for any new trace, the distance to the average is computed and compared to the threshold. If the distance is above the threshold, then this new trace is considered anomalous. So we've put the boot process verifier, the BPV, to the test in a case study on networking devices with 4 machines, 2 routers, and 2 switches. So the attacks are firmware replacement with OpenWRT for the routers and firmware downgrade for the switches. And we collected 500 boot up sequences per attack, but as I said, we only used 10 per evaluation for training. So the results are currently very satisfactory with for this first experiment with an overall F1 score of 0.942. thanks to the great consistency of the power pattern during the boot sequence, especially on simple networking devices. So the changes in firmware, even from 2 different firmware versions that were correct, could be correctly detected most of the time. These results are very encouraging, but we plan on expanding the experiment to include more types of machines and more attacks in the future. Thank you for your attention, and please ask me if you have any questions.
Thank you very much for this talk. Interesting. So is there a question in the room? Yeah, so then I have a very short question. I mean, in fact, this works because attacks have not been trained for this kind of detection, because maybe if you can train your attack also in the sort that you will not detect it.
Yeah, so the idea of using side channel power is that it is, at least currently, not easy to obfuscate the power consumption of a program. If you want to make significant changes to a program, you will have to have different power consumption.
Yeah, of course.
There may be a way to train or to design a program that would have a different effect with almost the same power consumption. But thanks to, as I said, the great consistency of the boot up sequence, the boot up sequence uses not a lot of optimization. It's a lot of simple operations. So the power consumption, especially on simple devices, is very consistent, and that allows us to detect most of the configuration change or code change or even hardware change that you could put on a networking device in this case.
Okay, I see. This looks for this application kind of appropriate method. Okay, so thank you very much. So we come to our last talk by Jean-Baptiste Janin from University of Michigan towards a theory of robust quantitative semantics for signal temporal logic.
Okay, thank you, Suzanne. Can you hear me?
Yes.
Okay, thank you. So quantitative semantics for signal temporal logic are useful to solve optimization problems, in particular in the fields of falsification and control synthesis of dynamical systems. Concretely, given a formula and a trace, the quantitative semantics doesn't just return true or false. The quantitative semantics will return a number that gives you an idea how true it is, what margin this is true. For example, some semantics will use like the maximum, and some other semantics, more recent semantics, will use sums or other operators. In this paper, we're interested in understanding how to generalize those quantitative semantics and how to give precise conditions under which those semantics are sound. So the standard quantitative semantics of Finicos and Papas in 2009, and then also developed in another paper by Donziel and Mahler, which are 2 foundational papers for quantitative semantics for signal temporal logic. They mainly use the maximum. And of course, here I'm only showing just a few operators. Of course, everything generalizes to all the operators. And they use the maximum. And in particular, for an or a finally, we're going to use the quantitative semantics for an or is going to be the maximum of the quantitative semantics of both sides. The quantitative semantics of a finally will be the maximum over the length of the time, and this of I, and this gives you a good idea of using the maximum. Says, okay, if my maximum was really high, then I'm very true, but it doesn't tell you how long the maximum was reached, and sometimes you're interested in knowing how long it was reached. Another idea that was more recent, that was proposed in several papers, is to use the sum. And so instead of to be able to say fine psi are both true, then or is very true, we're going to use the sum, and we're going to use the same idea for finally. In this paper, we propose to generalize by taking those maximum and sums to abstract operators, nu, beta, and gamma, and we're trying to understand what is necessary on those operators for the semantics to be sound. So soundness, what does soundness mean for quantitative semantics? Quantitative semantics, soundness means that if my quantitative semantics is strictly positive, okay, then my property is satisfied. And we're trying to understand which properties of those operators are sufficient to achieve soundness. In particular, for beta, for nu, for example, the sufficient condition is that if nu of x is strictly positive, which if nu of x is strictly positive, it basically tells you that the quantitative semantics is strictly positive. Then we want the inside to be strictly positive. And the intuition is that it has to be able to be satisfied, it has to be strictly positive. That's the intuition. For an OR, we want, if the beta is strictly positive, we want one side or the other to be strictly positive. And the intuition here is that if the quantitative semantics on the OR is strictly positive, we want the quantitative semantics on one of them to be strictly positive, which allows us to prove that one of them is actually true. And we have something very similar happening on finally. So this generalization, using this generalization, we've implemented using the tool Breach several quantitative semantics, and we've run some small experiments, some starting experiments. And a few takeaways from those experiments is that things like benchmarks like fuel control and autotrans, they're falsified by extreme values, and those extreme values typically in Breach are tested early. And so this is why we have very small number of iterations. But Telex, in the last two benchmarks, Telex, which is a semantics that was proposed very recently, sees much higher iterations, and which we think this is because that semantics favors tightness over robustness. And that's all. Thank you.
Thank you very much for this talk. Yes, interesting. Is there any question in the room?
Yep. So.
Yes, Rose.
Yep. Hi. So my first question, since we haven't seen each other in a while, would you like to set up a meeting, Jean-Baptiste, to talk about research sometime? Second question. Second question. You gave a bit of an example of different semantics that could be used in Breach and whether they were sound. I guess, could you help give me a sense of, are these semantics where there's already an understanding that they're sound, but now we have a proof, or is your goal more to establish what it takes to be sound, and that allows you a lot more freedom to experiment with which semantics you're going to use?
Yeah.
So on the first question, sure, I'd be glad to talk more about research. On the second one, so our experience going through a bunch of papers that develop new quantitative semantics is that some papers will not be sound. Some papers are sound and prove that they're sound. Some papers pretend to be sound. Like there's a theorem in the paper that says it's sound, but actually it's not. And I think a lot of those proofs are done. I mean, I guess they're not done properly. We found at least two papers where the proof of soundness was incorrect. We've emailed the authors, actually didn't get back to us, but we tried. And then some papers don't even try to do soundness, or they establish a theorem of soundness, which is kind of contrived and doesn't seem to be the right way. So we're trying to clean up all this, basically. The idea is that there's been a lot of there's been a number of quantitative semantics that have been developed recently. And there's one by Haswell, there's a bunch by Belta. I mean, you have the references in the paper. And we're trying to see, okay, what are the fundamental ideas and how can we achieve soundness, and how can we, a lot of those semantics have common things in them, but we're trying to make sure things are straight and things are sound. And if soundness is not achievable and it's not important, that's a discussion we can have. But we don't want to see papers where people pretend to be sound where they're not actually sound.
Great, thank you.
Okay, thank you. Yeah, this seems okay. There is an interesting discussion to be had, but I think we should have this now offline because our budget is exhausted. So thank you to all of you, and see you at one of the next sessions. Thank you.
Thank you, Suzanne.
Thank you, everyone.
Bye-bye.
Bye-bye.